Okay, welcome to today's session on time when it's supposed to happen, which is always great. So 2 o'clock here on Tuesday, and we're going to get started. So what we're doing this week, 3 sections, 13, 14, and 15. Section 13 will go fairly quickly. It's its own beast, I guess. And then 14 and 15 really do kind of go together and they're interwoven. If you have your formula sheet near you, so that page 245 from your packet, we will be getting into that with section 15, so it'll be good. The way this week falls, you actually have 2 quizzes, because again, this course is condensed into 12 weeks from our 16-week counterpart. Just 1 discussion board. You have an Excel assignment with histograms. I will be posting a video. That Excel assignment, you're going to be creating a bar graph and or a histogram, depending on what you think you need from your data. So I have 2 videos, one that shows how to create a bar graph and one that shows how to create a histogram in Excel. If you need those, you have them. If you don't need them, you already know how to do it, then great. So when I post the live session, as I always do, I will post those Excel videos as well. So just be looking for those under the announcements after class. So yeah, so we have that. Project 2 was announced last week. I think I did post videos for that as well. If I didn't, let me know and I will. But you want to kind of start working on that. Due date for Project 2, it's on here somewhere, is the 15th. So it's the week after the exam, but you still want to kind of maybe get started thinking through it. And then have you scheduled exam 2, right? We don't want to get into that, oh crap, it's the last day and I have it scheduled, because then you're in trouble. So I'm pretty much out of being nice at this point in the semester, so make sure you don't have to ask for an extension because you forgot to schedule. So it's due November 11th. So that week will be exam week. So go ahead and look at your schedule, figure out what day works best for you, and get that scheduled. That'll make your life just easier in the long run. So before we get started into section 13, do any of you have any questions? Feel free to throw them in the chat box, or you can verbalize, whatever is easiest for you. Nope, Trent says nope. Okay, well, at any point in time, if those questions come up, just go ahead and shoot them at me and we'll go from there. So we're going to go ahead and start into section 13. So we have bar graphs and histograms, and I'm not sure if you have or you know the difference between them, but basically a histogram is a type of bar graph. So when we talk about a histogram, it's a special case bar graph. And the difference is that a bar graph deals with discrete data. And when I talk about discrete, I'm talking about things that are separate from each other. So if we would talk about like the number of runs the Yankees scored in a game. Well, you can score 0 runs or 1 run or 2 run or 3 runs, but you can't score 1.5, right? So when you think about discrete, you think about almost counting, perhaps. Or we also sometimes call this categorical. So if we were going to make a bar graph talking about the color of cars in the parking lot, blue, red, black, gray, silver, whatever, those are very concrete, right? They're discrete, they're different. They don't run together. They are what they are. So that's a bar graph. And the big thing about bar graphs is the bars do not touch, because we're talking about discrete data. So the bars don't touch, there's space between them. That's kind of a big thing. All right, so now when we talk about a histogram, now we're talking about continuous data. So data that flows nicely from one to the other. So think about age or liquid, right? In my water bottle, I could have 1 ounces or 2 ounces, but I also could have 1.1 ounce or 1.234 ounces. So when you have all of those decimals in between your concrete numbers, that's continuous data. We also talk about a lot of numerical data is continuous, right? Still has to be continuous data, but that's another way we think about it. And the big thing here is that the bars do touch. And they touch because there's fluidity within your data. And that's the big difference between the bar graph and the histogram, is that in a bar graph, the bars do not touch. In a histogram, the bars do touch. And it's because of the type of data. So I encourage you to watch the video that goes with page 111. I don't remember why, but there's 3 exclamation points. So when I made this PowerPoint, I thought it was important. So you might want to do that. But we're going to go ahead and get to an example here. Drawings. So we're going to create a graph that goes with ages of participants in the talent show. So if we're talking about ages, are we going to create a bar graph or a histogram? Would age be continuous or discrete data? Kara says histogram, and I agree, because a histogram talks about continuous data and age is continuous, right? Like, at what point do you go from being 35 to 36? Is it really the day of your birth? Or at 35 and a half, does that round up, right? Depends on how you look at it. All right, so we know that we are going to create a graph that the bars touch. So look at your smallest age, right, is 3. So we're going to have a bar that's 3, a bar for 4, and we're going to go all the way up to 9. And we're going to create a bar graph. And I really assume that you can all create a bar graph. You know, count them up and you create your bars. I have a lot of confidence in you. The one thing I want to stress is that you want to have a title and you want to label your axes. And in this case, these are ages and my title is age, right? On this side, I would have maybe frequency. And so you want to make sure that you have your labels on your graph and your numbers. And again, I know that I'm flying through this section or this particular spot, but I do believe that you guys can create a graph. So this is what our bar graph or our histogram would look like from that data. Okay, you can see it goes up. We would say, oh, never mind. I'm getting myself ahead of this. So we want to find the mean and the median from this distribution. You know, when we're given, dang it. When we're given a bunch of data, I know that you guys can find the mean and the median of this data, right? We've done that. We did that in section 8, where you can add them all up and divide by how many there are. But when you get to a larger data set, and I don't even know if this is considered large, but when you get to a larger data set and you're trying to find the mean, you're more likely to type a number in wrong, miss one, right? Just those little things that can make a huge difference when it comes to doing this mathematics. And the same for the median. We talked about putting them in order least to greatest. Well, there's a lot of numbers, and that just gets to be a lot of work. So when we put this into a lovely histogram first, or graphical representation, it can be a little bit easier to do these things. So when we want to find the mean, a way to do this is to think about, okay, in this first graph, that's a 3. The age is 3, and there are 3 kids that are 3. Well, if I have 3 kids that are aged 3, that's 9 total years, right? 3 times 3. My 4-year-olds, there are 6 of them. So 6 times 4 is 24. So this is just like the total ages of all of the kids. Then I have a 5 times 7, well, that's 35. 6 times 2 is 12. 7 times 5 is 35. 8 times 3 is 24. And 9 times 2 is 18. Now, this is only easier if you can multiply. Although you have calculators. Okay, so now when I'm thinking about this, if I add these ages up, now I'm adding 7 numbers together instead of, I don't know, we got to find out the total here in a minute. So when I look at all of these, that is not my data set. There it is. Okay, so when I add these all together, is anybody playing along? Do you guys have these added together? It's okay if you don't. I'm kind of just talking fast. When we add them all together, we have 157. So that's the total ages. If I would have added all of those numbers on the previous page, if I'd have added all those together, I'd get 157. And now it comes back to just finding the average, which we divide by how many numbers we have. And there were 28 on that previous page. I know because I have that written down. So if we just think back, 7 times 4, there's, right, because Gosh darn it. There's 28 numbers here. So if I take my 157 and divide by 28, that will give me the average. So the mean from this is approximately 5.6. And you might say, Becky, that's actually more work than just adding them all at the beginning. Sure, maybe it is. And there's no right or wrong way to do this. So if you're doing it by hand, you can do it whatever way your heart desires. It's my job to just give you other options, right? So we have ourselves the mean. Any questions on that process of finding the mean? Oh, great. So now we are going to, so the mean was 5.6. Now we're going to use the graphic to find the median. And if you recall way back when, finding the median meant working your way to the middle number when your numbers are in order least to greatest. Well, if you look at this, our numbers are in order least to greatest. They're just in piles, right? So this first pile, I have 3 numbers here because it goes up to 3. So if you think about what we did, right, in terms of crossing off to get to the middle, if I take away one of these, one small number, I get rid of one big number, right? We cross them out, working our way to the middle. And we can do that again and again. Okay, I have another 3-year-old. I have another 9-year-old. Now I'm done with my 9-year-olds. So I still have a 3-year-old. And now my oldest kid is 8. And I do this all the way until okay, done with 3, I go to 4. I'm still at 8. And we do this till we get to the middle, right? Still at 4. Now we're here. And if you're like, man, this is going to take forever. Well, sure. And you can do, a couple at a time. If I look at my 7-year-olds, I have 5 7-year-olds. So if I get rid of 5 big numbers, I'm going to get rid of, I have 1, 2, 3, 4, 5. There, right? So I did a couple at a time. If I go, okay, now 6-year-olds, I have 2 6-year-olds. So get rid of 2 of those, 2 of those. You'll notice the only age I have left is 5. So my median is 5. Right? But you can cross them off, big number, small number, work your way to the middle, just like we did when we had them written down in order. Now we're just doing it with boxes instead of numbers. Okay. Now, the second part of this question, what does that tell us about the distribution? If our mean is 5.6 and the median is 5, so the mean is greater than the median, what does that tell us? This goes back to section 8. Anybody remember? Look at the way that this is pointing. If it's pointing to the right, what does it mean? This would be skewed which direction? Exactly, Kara. It's skewed right. So, and that's why we put the inequality symbol there. Mean versus median. If it's greater than, right, points to the right, it's skewed right. And if you just look at your graphic, let me get rid of these drawings. The tallest bar is here. Okay, well, if I go to the left, there's only 2 bars to the left. But if I go to the right, there's 1, 2, 3, 4. So there's more bars to the right, so that also tells me it's skewed right. So our mathematics, the mean and the median, and the pictorial representation both agree that this would be skewed right. There's section 13 in a nutshell. Any questions about bar graphs or histograms? Okay. In that case, let's move on to section 14, the normal distribution. When we're talking about the normal distribution, and this is super hard to draw with a mouse, that's supposed to be a straight line. The normal distribution is a bell curve, and that might be the best bell curve I've ever drawn with a mouse. The thing about a bell curve is all of the data will fall underneath, right? And all is 100%. If I cut a line directly down the middle, pretend that's directly down the middle, it would make it symmetrical, right? The right and the left side would be exactly the same. So this is 100% of our data. It's symmetric about the mean, which means this green dotted line is where the mean comes in. So the mean, the median, and the mode would all fall directly in the middle. Now, it's also true that the area under the curve, so all of this space underneath here, is equal to the probability. So when we talk about what is the probability of blah, 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 well, if you can find the area under the curve, you have found probability. Okay? And if you think about it, if all of the data underneath there is 100%, then if I just find this piece, well, that would be, part of the whole, which is a ratio, which can be written as a probability. So that's kind of going to be the mindset through the next two sections, is that probability, proportions, percents, I call them the 3 Ps, they're all meaning the same thing, which is the area under the curve. Okay, one other thing that I want to throw out at you before we move on is that if we have two, okay, so we're going to get to talking about standard deviation. Standard deviation talks about how far the data is from the mean, or actually how spread out your data is. So, we know that in a normal distribution, the mean is in the middle. And you can see how this one is high and tight. Most of the data is fairly close to the mean. So this would have a small standard deviation, which is this is a sigma, is the Greek symbol here. In this one, which I would call, flat and fat, well, the data is more spread out. If you have a spread out data, you're going to have a big standard deviation. So when you look at your graphic, if your graphic is tall and skinny, your data is hovered around the mean, you have a small standard deviation. Short and fat, very spread out, you have a big standard deviation. Just to kind of give you a visual idea of what it's all about. Okay, so standard deviation really talks about the spread of your data. Depending on what you're talking about, sometimes you want a big standard deviation, sometimes you want a small standard deviation. Really depends on what you're doing. So, okay, let's get into, that's the wrong button. There we go. The empirical rule. Okay, so section 14 and 15 both deal with the normal distribution and finding probabilities. The difference is that section 14 talks about the empirical rule, and the empirical rule is an approximation, and that is kind of a big thing to remember. And it's really a limitation of the empirical rule, is that it's not very accurate. So if you're just looking for a quick and dirty way to approximate some probabilities, the empirical rule might be your friend. But you're going to see pretty quickly, I think, how limited it really is in terms of its use. But I want to show you an example of what it is and how it came to be. Wow, that's a horrible line. I got to try that over. There is a video called The Empirical Rule that I have as part of your class. And it's a pretty good video. It's 2.5 minutes long. And it does the exact same thing I'm going to do here. If for some reason it doesn't make sense to you and you're like, yeah, I need to see that again, you can just watch that 2.5 minute video and it will just kind of refresh. Okay, so we're going to do this example with a mean of 70, a standard deviation of 5, because I'm a concrete person. I like to see examples with numbers. Abstractness doesn't really work for me. So we're going to talk about this in the abstract and with numbers so you can kind of see the connection. And with that, I'm kind of getting excited and getting ahead of myself. The empirical rule is often also called the 68, 95, 99.7 rule. And you're going to see why that is here in just a second. It's all going to come together. Okay, so we know this is a normal distribution. So what goes in the middle? What does this green line represent? Very good. The green line is the mean. And that's always where we're going to start. You always got to start in the middle. And we know for our concrete example that the mean is 70. So I'm just going to do the numbers right underneath our abstractness. Okay, according to the empirical rule, 68% of our data will fall within one standard deviation of the mean. So if I go one standard deviation on either side, that's 68% of our data. Okay, so if I go to the right, think of this as a number line. If I go to the right, I'm going to add a standard deviation. Well, the standard deviation is 5, So what would my value be one step to the right of the mean? $75. Very good. And if I go to the left, I'm subtracting, so that value would be 65. Exactly. Okay, so empirically, the empirical rule says 68% of the data falls between these two numbers. Well, remember the mean splits it in half. So from red to red is 68% of our data. That means each side is 34% of our data. So if we said these are test scores, then we could say 34% of people score between a 70 and a 75, because between those two values, that's the percent. And these would be probabilities. Okay. Now, the empirical rule also says 95% fall within 2 standard deviations of the mean. So if I take the mean and I go another standard deviation out, so now I'm 2 standard deviations away, what's my new value there in orange? 80. Good, because as we go to the right, we simply add a standard deviation. And as we go to the left, we subtract, and that would give us 60. So those would be the test scores. Between 60 and 80 is 95% of our data. Right? By the empirical rule, 95% of the data falls between 60 and 80. Okay, so let's think about what goes in these two orange spots. Well, if from orange to orange is 95, but remember, I've already counted for 68 of that from red to red. So how much do I have left? What's 95 minus 68? $27. Perfect. And again, we know this is symmetrical. It's got to be even on both sides. So we would divide that by 2 to find out that 13.5% fall on each of these spots. So if I said, what's the probability of finding a student who scored between 75 and 80? Well, that would be 13.5%. All right, so far so good. Now, 99.7% falls within 3 standard deviations of the mean. So if I add another one, I'm at 85 on the right. I subtract another one, and I'm at 55 on the left. So I know that 99.7% of my data fall 55 to 85. Same concept. If the whole thing is 99.7, we know that 95 is accounted for orange to orange. That means I have 4.7% left to be split into 2 sides. So each of these is 2.35%. So what's the probability of picking somebody who scored between a 55 and a 60? Well, that would be 2.35%. Okay, now the last piece is that you'll notice we have what I call the wings. So the pieces out here, because you can score less than a 55, you can score higher than an 85. The whole thing, remember, is 100%. And we know that 99.7 is taken care of purple to purple, so I've got 0.3% left, meaning 0.15% is left in each wing. We call these unusual. That's 0.3% of the data. It's very unusual to fall outside of 3 standard deviations of the mean. So if you look in your packet, you see this normal distribution curve with these percentages in it. And I like to explain how they got there, why they're there. I do not know how these numbers came to be, like who picked them. I'm sure there's math or written about it somewhere. But you could say, what's the probability of picking somebody between 60 and 75? Well, here's 60, here's 75. If I add up the pieces in between, well, 68 plus 13.5, it's 81.5% chance. Boom. Quick way to estimate what's going on here. Can any of you see a limitation to the empirical rule before we do an example? Nobody? Nothing? Well, if you think back on your exam, right? Based off the empirical rule, we have 7 values. And that's it. If you scored an 82 and you want to know what's the probability of scoring greater than an 82, well, an 82 is somewhere in here. I don't know what percentage that is because it's right, kind of in the middle there of 2.35%. And this is a curve, so it's not perfect and you don't know what's where. So really the empirical rule is great for 7 pieces of data. And anything outside of those 7, it doesn't really work. So then you would have to round and then you get more approximate, right? So you're not very exact when you're using the empirical rule. And that can be a big limitation, is that it's very much an approximation. But okay, let's go ahead and do an example. The average mile per gallon in luxury cars is 29 with a standard deviation of 3. So we're going to draw a normal distribution curve, labeling through 3 standard deviations from the mean. And then we're going to answer 4 probability questions about it. Okay, and I think I have those on different slides. So, yep. So first what we're going to do is we're going to draw a normal distribution curve. And when I say we, I mean you. So I want you to do just what we got done doing. You're going to get yourself a normal distribution. That's a pretty straight line. And you're going to fill them in, going 3 standard deviations in each direction. 1, 2, 3. And again, the mean was 29, and the standard deviation was 3. Okay, so I'll give you a minute. You might want to put your percentages in too for the empirical rule after you finish. That's the one nice thing about the empirical rule, is that the percentages are always the same. Okay, you guys got your numbers in? Okay, great. So I'm not going to spend a ton of time here, but right, 29 goes in the middle, 32, 35, 38, 26, 23, 20. Questions on those? Okay, great. Let's move on to the next question. Let me get rid of this. All right, so we're going to do B and C at the same time. So probability a car gets less than 23 and the probability a car gets more than 23. So when you're thinking about this, right? Whoa, that's horrible. But 23 was down here. So part B says less than 23. So we're looking area to the left. So you would add up all the percentages to the left. What is the total of the percentages to the left of 23? .5, excellent. So the answer to part B would be 2.5%. All right, then part C says, well, what about more? Well, more means greater than, so it's going to be over here. So you've got a couple different ways you can do it. One, you can add all of those percentages together. True. What's another way you can find the other area to the right? Anybody think of another way you could do it? Subtract from 100. Perfect. Jacob, you got to subtract from 100. So the whole thing, right, is 100%. Well, if 2.5 is to the left, then all of it minus 2.5 would be the area on the right, which would be 97.5%. We call these complements. So if you split something in two, the two sides added together to be 100% are complements. So that's a concept, subtracting from 100%, that we're going to really take into section 5. It's going to be very, very important. So the answer to letter C is 97.5%. Stop me if you have questions, but it seems like you guys are grasping this pretty well. Okay, so let's go to the next page. So now we're talking about between 20 and 32. So if you have your picture, you locate 20, which is way down here. You locate 32, which is about right here, and it's between. So you're looking at just the percentages that are between those two values. So there's really, I mean, you add these up. You rounded, right? Who was it that rounded? Kara, you rounded. You want to not round as much as possible because you're already approximating. So Jacob, yep, you're a little bit more exact, 83.85% from 20 to 32. Okay, everybody see how Jacob got that? He took the 2.35 plus 13.5 plus 34 plus 34. Okay, good. Right? And so once you understand what the empirical rule is, it's really not bad. All right, so letter E, the last one, how likely, this is another word for, you know, what's the probability a car gets more than 38 miles per gallon. Well, 38 is way over yonder, and we're talking more, so that's area to the right. So what is the probability? What's the percentage to the right of 38? 0.15%. There you go. So it's not very likely. I mean, 0.15% is a very, very low percentage. So you can say that's just not very likely for that to happen. Okay. Questions about the empirical rule, how it works, what it is, any of the above? You guys feel okay with that concept? Okay, we're going to go with yes. Okay, good. I got a yeah. I'll take that. All right, so let's then move to section 15, which is z-scores. Okay, so the empirical rule, right, the limitation is that it's an approximation. You only have those 7 pieces of data. It's very limited. Whereas z-scores allow you to do the same thing. We're going to deal with normal distributions. We're going to find probabilities. We're going to use that bell curve. But we can do it a little bit more exact. So the first thing, there it is. First thing I want you to do is I want you to look at your formula sheet that I asked you to have out at the beginning and flip it over. So I think you're on page 246. You should see a 4-column table that within each column has 2 columns. Right, the left side says z-scores and the right side says probabilities. Does everybody see that? Can I get a yeah from everybody if you have your formula sheet and you see what I'm talking about? Because this is kind of the big piece here. If you can do the math, that's great, but if you don't know how to use the table, you're pointless. Okay, so we've got a Kara and a Jacob. Trent and Christian, you guys playing along? You with me? Trent says, yeah. Okay, so there we go. All right, excellent. Thank you all for being here and participating. I appreciate it. Okay, so that table that we're dealing with, and here first we're just going to talk about the table. So the table has a bunch of z-scores, and even this is a pretty small, table. Okay, so a z-score. What is a z-score? Well, a z-score is a way to standardize your data. So a real life story of how this might be important. So when I did my dissertation last year, I was looking at placement test scores for students over a 4-year period. And in that 4 years, we changed placement tests. So we had the compass test, which had one scoring metric, and then we had the AccuPlacer, which is what we use now, with a different scoring metric. So the mean of one was like an 80, and the mean of the other was like a 52, but it meant the same thing. Well, just if you put an 80 and a 52 into the system, it doesn't read it as the same thing. So in order to be able to use this data, I had to standardize it. I had to find a way to make the compass scores and the AccuPlacer scores kind of mesh together. So what I did is took all the compass scores, and I found the mean and the standard deviation, and then I changed them all to z-scores. And when I say that, the z-score has a mean of 0. So if we're talking about z-scores, in the middle where the mean is always 0. So if I took compass, changed them to z-scores, now instead of having an 80 for a mean, the mean was 0. Then I took my AccuPlacer scores. I did the same thing. I found the mean, the standard deviation. I turned them all to z-scores. So now the mean for both sets of data was 0. So now the data lined up. Now I could play with them together because they were all z-scores. So it's a way to standardize. So when somebody says, I had a z-score of 1.4, well, if it's positive, that means you're greater than the mean, because remember, the mean is 0. Right? The mean is always 0 when you're talking about z-scores. And if you're 1.4, a z-score of 1.4 means you are 1.4 standard deviations above the mean. So whatever your z-score is, that's how many standard deviations you are away. So if we have a z-score of negative 2.3, that means I am 2.3 standard deviations below the mean. And I know it's below because it's negative. Okay, so that's kind of what a z-score is and why they're important. A lot of data sets, when you are working statistics, they are important. Okay, so how to use this table. So let's go back to a z-score of 1.4. Let's say we took a test and we found out that on the test, Kara's z-score is 1.4 in terms of her grade. Well, that means that she scored 1.4 standard deviations above the mean. Whatever the mean was, whatever the standard deviation, she scored 1.4 standard deviations above the mean. That's great. Well, what's the percentage of people, or the probability of people who tested below her? Well, if Kara is this line, below Kara in terms of scores on the test are all of these people to the left. Now, the table that you have in front of you always gives area to the left. So if you look, find the z-score of 1.4. It's in the 4th column. What is the probability that goes with a z-score of 1.4? Very good. So 0.9192. So that's a decimal. We can change that to a percent, right? That's 91.92%. So we would say that 91.92% of students scored lower than Kara. That's what this means. Now, let's go one step further and think back. What percentage of students scored higher than Kara in this example? How do I find that pink area? Think about what we did with the empirical rule. If the total area under the curve is 100%, which is 1 as a decimal, we're going to subtract exactly. So you can either do it as percents, 100% minus the 91.92. Sometimes you might not have percents. So remember, 100% as a decimal is just 1. So 1 minus 0.9192, you'll get the same answer, right? As a decimal, 0.0808, or as a percent, 8.08%. So the concepts of section 14 and 15 really go together in terms of right and left side. You just have to remember the table is always area to the left, always. If you want the area on the right, you have to subtract from 1. I'm a big fan of drawing pictures when I do these problems, because when I read it and it says find the probability that more than, well, that's area to the right. And if I draw a picture and I just shade it in, then I don't accidentally just give the area to the left, because the table gives me to the left. So you really have to be aware of the details and what's going on. Okay, so let's go ahead and turn the page. The formula in the table, well, we've already talked about the table, so that's good. So the formula, you will see that this formula, z equals x minus mu over sigma, is right underneath that table on page 246. So it is on the formula sheet. But if you don't know what those things mean, it's pretty useless. So the z stands for the z-score. X is the value. Mu is the mean. And sigma is the standard deviation. So the value is usually what you're trying to evaluate. You're trying to figure out, you know, how it measures up against the mean and the standard deviation. You know, they're going to tell you the average is this, the standard deviation is this. So they give you, generally, they give you the mean and the standard deviation, and you got to, you know, so it's pretty easy to locate which one is the value. So, all right, let's do some problems. We've had enough chitty chat. We're going to get practice with this formula as we work through. So we have letter 9A. And we're going to use this data. The average is 460 with a standard deviation of 35. And of course, this is completely made up data. So average calories burnt at the gym is 460 with a standard deviation of 35. And we're going to use these for the next few problems. So first, we're just going to find the z-score of somebody who burnt 510 calories. So if this is the you know, what we're trying to locate, right, this is our value. Because we know this here is our mean, and this part here is our standard deviation. So when you plug it in, value minus the mean over the standard deviation, one thing I want to highlight is that depending on your calculator, you might, and how you punch into your calculator, you might want to put it in parentheses first. If you don't and you just type it in as you see it, some calculators will divide and then subtract, and that's not what you want, right? You want the order of operations to subtract in your numerator first and then divide by 35. So what will our z-score be for this particular exercising individual? .43. Very good. And now this kind of draws us to, and we're gonna get into this more on the next page. But if you look at your sheet, your table, 1.43 is not a possible z-score, right? You're gonna have to round for some of these, and you just round, right? Normal rounding rules apply. Go to whatever is closest, and we'll go from there. Okay. If you have questions at any point in time, just stop me. Otherwise, we're just going to keep motoring. Okay, so we're going to use the same value of 510. Carriage has told us that we have a z-score of 1.4. Wow, same one I used earlier. So your first step, what is the probability of someone burning less than 510 calories? Well, your first step is always to turn it into a z-score, because you know how to standardize with the z-score. You have probabilities that go with a z-score. So when we have a z-score of 1.4, we know that's to the right of the mean because it's positive. If I'm burning less, do I want to find the area to the left or the right of my z-score? To the left, exactly, because less is over here. So we've actually already found 1.4 because we did that in our last example. But if we want area to the left, we pick that straight up off of our table. And as we found on the last example, we're at 0.9192. All right. And unfortunately, if you look at the next problem, which is more, I'm kind of kicking myself now that I didn't preview my numbers before we did this problem. More is on the other side, right? Just to reiterate, we subtract from 1. And that gives us 0.0808. Okay. That's just basic. So now I'm going to have you guys do one. Okay. Start to finish this next problem. Okay. So you guys are going to try average calories burned at the gym is 460 with a standard deviation of 35. What's the probability of somebody burning less than 400? I'll give you a few minutes and then we'll chat about it. All right, what did you do first? Find the z-score. Beautiful. So value minus the mean over the standard deviation. What'd you get for a z-score? Negative 1.7. Beautiful. Okay, so if you draw a picture, negative 1.7 is below the mean, so it's going to be somewhere over here. Are you finding area to the left or the right? To the left. Great. So then you look at your table, and what do you get? Perfect. 4.46%. You might have written that as a decimal, 0.0446. I want to tell you this right now. Read the directions in WebWork because your table gives you 4 decimal places, but sometimes WebWork asks it for a decimal to, or as a decimal to 3 decimal places, and you have to round. So I've gotten a lot of questions from my 16-week classes of, I'm doing this wrong. No, you just can't read directions, right? So make sure you really read the directions for these because you'll know how to do it. It's just, you got to make sure you're putting it in the right way. Good. All right. So it seems like you guys know, or you understood a little bit what you're doing. I appreciate that. Good. Any questions on that particular problem? Okay. Then we have one more, and then we're done. So we're still at the gym, but now we want to find the probability of finding somebody that burns between 440 and 500. So now we're looking between. We want to find an area between. So the first thing, we still have to find z-scores. Okay, so I'm going to ask you guys to do that. Please find me 2 z-scores, one for the value of 440 and one for the value of 500. You can just type them in the chat box when you find them. Negative 0.6, oops, forgot my negative, and a positive 1.1. Fantastic. Thank you. You might have gone to negative 0.55. That's fine too. Either one is fine. This would be one where you just want to make sure you have your work shown. All right, so we want to find the area between this. And again, we're dealing with a curve, so it's not like you can just count. So the process, if you think about it, what you know is area to the left. So I know from this spot all the way to the left, if I look, what is to the left, area to the left of negative 0.6 for a z-score? Okay, so 0.2743. So the area to the left of my 0.6 is 0.2473, 2743, blah, 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 blah. Yes. Okay, then if I say, okay, well, area to the left of 1.1, that's all of this. What is the area to the left of 1.1? .8643. Okay, now with this image, you see that orange is all the way to the left, blue to the left, but we only want this spot up in here. How do I do that mathematically? Subtract. Exactly. If we subtract, the part that they share will go away and we're just left with the overlap. So I would take my 0.8643 minus 0.2743, and I'm left with 0.5900. So that's this piece in the middle. So there's a 59% chance of finding somebody who burns between 440 and 500 calories at the gym. And that's the process of using z-scores to find the probability between two values. That, my friends, concludes the day. So 3 sections, 13, 14, and 15. Remember, you have 2 quizzes this week, a discussion board and an Excel assignment in histograms. I will post the videos that will help you with that if you get stuck, along with this live recording after they all load. Any questions for me at this time? Okay. Well, I'll stick around for a few. We got 6 more minutes till 3 o'clock, so I'll just stick around for a few more minutes in case you find any. Otherwise, you're free to go. Thanks for coming and participating. I greatly appreciate it. And as usual, if you have any questions throughout the week, just shoot me an email. But have a good week, and thanks for being here.